selfish in choosing these topics because I really would love to have feedback from you all on it. So Okay, so this is a quick outline of the first part of the talk. And again, some of you in the room may be experts on this and know more about it than me. I'll just give a quick introduction to post hoc interpretability methods for machine learning and describe why we might want to have a new approach. I'll talk about how we're going to approach this using the Fisher information matrix, and then just show a few preliminary case studies, give you some idea about how it works. Okay. Um, Okay, so let's talk about traditional post hoc interpretability networks. The goal is to explain a pre-trained classifier's decision, right? We'd like to get some insights into what features were important in making a decision. This is very important for medical imaging applications so that there can be some trust, right? It's hard to have trust if you don't have any idea how the model is working, right? And I think a lot of you are familiar with this. There's a whole industry, from what I can tell, of methods. People have made careers out of developing methods, such as GradCam, saliency maps, and other feature attribution methods. And there's also a different category of methods based on perturbation analysis or occluding parts of images to try to get insights into what part of the input was really important to the classifier in making a decision. Okay. So there are some limitations, as far as I can tell, to some of these existing post hoc interpretability methods. A lot of them, perhaps not all, but a lot of them I would say are not theoretically grounded. They're based on certain heuristics and design choices. Some of the methods have shown to be insensitive to adversarial perturbations. So if you add an adversarial perturbation to the input image, it doesn't change the interpretability map, and that doesn't seem quite right. Also, again, there's a whole library, a whole category of different methods, and sometimes they don't produce the same interpretability maps. So they don't always agree with each other. That's not necessarily comforting either. So, I think there remains a need for a more theoretically grounded interpretability framework. And so here's kind of a table to kind of tell you what our goals, what our objectives were. On the left-hand column, these describe kind of the traditional, or again, at least most of the traditional post hoc interpretability methods. They can be heuristic, and in general, they create heat maps that you superimpose on an image to reveal what regions of the input image or what groups of pixels were important. On the right-hand side, in the right column, these are some of the features of the method I'm going to describe. It's tied to the local decision geometry via analysis of an input-dependent Fisher information matrix. And instead of just producing a heat map that you superimpose onto your input image, we seek to actually rather decompose the input image via a vector space decomposition, where we can decompose it into the task-sensitive part and the part that was not task-sensitive. So that's the goal. So just to set the notation in the background, we're going to assume we have a probabilistic classifier. The coordinate, or the vector x, denotes the input to be classified image. Y is our task variable, and there could be C different categories. In some of the examples, I'll just let C equal to 2, and we'll have a binary detection class. So anyway, we assume we have a classifier that produces a predictive distribution, P of theta, over the task variable Y. Okay, so that's just standard setup. Okay, now let me define the input-dependent Fisher information matrix, and this is kind of the key tool that we had in our analysis. So let's consider that we have a trained classifier P. We're not going to fine-tune the classifier. We have a classifier P, and we have an image X that was classified, and we want to understand what parts of X were driving the decision. Okay? So this input-dependent Fisher information matrix, we'll call IFIM, evaluated at input image X, is defined by the equation given here. It looks very similar to the traditional definition of Fisher information, with a few exceptions. You notice that the gradient now is with respect to X. It's with respect to the input image. Traditionally, in the FIM, the gradient would be respect to the parameter that is parameterizing the distribution. So here we're taking the gradient with respect to X, and we're taking the average over the distribution of the task variable Y. Okay. But other than that, structurally, it seems similar to the Fisher information matrix, except now, again, we're interested in analyzing the sensitivity of our predictive distribution to perturbations of the input, right, which is X here, okay? So what are some useful features of this matrix? Well, it's positive semi-definite, so it defines a local geometry in the input space relative to X. The eigenvectors define sensitivity directions in the input image space. So large eigenvalues correspond to directions that strongly affect the predicted distribution. Small eigenvalues or zero eigenvalues are directions that weakly or don't affect the model's predicted distribution. Okay? So this induces a natural vector space decomposition of the input image. We can decompose it into components that are model sensitive versus components that are model insensitive. And this is the key observation that we seek to exploit. Okay? Here I've written down the IFAM in just a different in terms of different notation. So for a C-class model, we can just write it as a summation over the different classes, the probability P theta times GC transpose, where here GC of X is just shorthand for the score function for the gradient of X of the log probability. Okay. So in terms of this notation, the IFIM can just be written as G of X transpose. Okay? So there are some concerns about being able to construct this matrix and do singular value decomposition on it because it can be enormous, right? So there are some nice properties that might alleviate this concern to some extent, right? So there's a low rank property here. So the rank of this input dependent Fisher information matrix is less than or equal to C, where C is the number of classes. So typically C, the number of classes is much less than N. Here N is the dimension of our input image, or if you wish, the number of pixels in the input image. So that's a good property. So we can form a Gram matrix K of X as G of X transpose G of X. Now, instead of an N by N matrix, that matrix K is now a C by C matrix, which is usually tractable. You can do SVD on that. You can yield the positive eigenvalues of f of x, and we can obtain the corresponding eigenvectors of f of x by g, v, and gamma to the -1/2 power. Okay, so this provides some procedure for the dominant spectral recovery when class-wise input gradients are available and the effective class dimension is manageable. More generally speaking, then there are iterative approaches to this. So matrix-free methods become important when we can't explicitly compute or store that full gradient, or if the model output has a large dimension, such as structured outputs, or if it's a classification map or something like that. But in any case, we didn't explore this class of models yet, but in principle, matrix-free methods can be used to compute that dominant eigenvector structure, right? Without having to compute and store the matrix, just by using matrix-free methods, such as Lankos methods or randomized SVD. Okay, so let's assume now we've been given a classifier, we've been given an image X that was classified, we've constructed this matrix, and we've managed to compute the dominant singular vectors and eigenvalues. What's next? Now we can create these sensitive and insensitive subspaces that I mentioned, right? So if lambda I are the eigenvectors, u sub I are the eigenvectors, and here also R is the rank, or whatever cutoff you choose in terms of the magnitude of your singular values. We can project onto a task-sensitive subspace by forming the outer products of those eigenvectors and form a projector onto that sensitive subspace. And of course, we can project onto the orthogonal complement of that subspace as well. So what does that mean? That means that if I give you an input image X and I give you the classifier, now we can decompose that input image X into two pieces. And here I'm calling it again the sensitive component and the insensitive component, right? So this is kind of the crux. This is the essence of what we were thinking about for this new interpretability method, right? So instead of creating a kind of a post hoc heuristic heat map or a feature attribution map, we actually literally want to decompose the input image into two pieces. And so let me show you some examples of that. But first, let me just give some more intuition into the sensitive component of the image. So there's different things we can say about this, right? This is the image component that most strongly affects the classifier's predictive distribution, right? So in other words, if the sensitive subspace describes directions where if we applied small perturbations in those directions, it would have some significant perturbation on the predicted distribution, where the insensitive subspace does not have that property, right? You can perturb the image along those directions and the output distribution doesn't really change much. So this should provide an interpretable image level representation of the dominant directions of predictive sensitivity.
Number of passes by number of passes.
Of the input Fisher information matrix, or which matrix? Let's go back here, right?
By
Yeah, so I mean, so the dimension of the sensitive subspace, we'll go back here, would be well, the rank of the Fisher information matrix is less than or equal to C, the number of classes. Right?
how do you protect the image of like the images? 1,000.
Yeah.
C is 5. What is that?
Yeah. Yeah, so if C is 5, let's assume that we have 5 dominant directions. So there are 5 eigenvalues of that matrix that are non-zero or have significant values.
But I mean, even the UI is like the dimensionality of the UI is the number of classes, right?
No, it's not the number of classes used about. It's number of pixels. Yeah, that's right. Yeah.
So while we've paused here, so this, I assume some of the previous methods also involved taking gradients with respect to the input.
Yeah.
You're kind of collecting all those gradients and then doing orthogonalization of them by the SV, I guess, right?
Yeah, I mean, the traditional methods are not exactly taking these same gradients that we're taking now. They're not, yeah. I mean, they take gradients in different ways depending on the method, right? But none of them are, as far as I can tell, are actually forming the gradient of this log probability function like we're doing here. And that's really what's different here, is that we're actually forming the matrix and exploiting the associated vector space structure and that's kind of the piece that, as far as I can tell, the other methods are not using. Any other points of clarification?
Yeah. Ask maybe a high level question. Is how is that related to like because I know that there's some work on feature information for formal verification of neural networks.
Mhm.
As a field, but I mean, there are some methods, but they're not scalable.
Okay.
Yeah. And they also want to find like some guarantees or certification of some given inputs and also norm around that input where the output is, let's say, is always going to be have some confidence on the true class.
Okay.
I was just wondering if this can be used or you're aware of that. So.
Yeah, no, certainly, I mean, Fisher information principles have been used in all different types of ways, including analysis of the sensitivity of neural networks. That's for sure. From what I can tell, what's new here is that, again, we're just exploiting an input-dependent Fisher information matrix and doing a decomposition of that input image with the goal of trying to understand which parts of the image are sensitive, were sensitively viewed by the classifier. Okay, and yep.
Yes, this you mentioned about multimodal here.
Yes.
We consider for the different modalities, the data dimension will also vary, right?
Yep.
So in that case, are we constantly like combine them together, or how can we handle this kind of the difference across different modalities?
Yeah, I mean, this is something that I recently started to think about, and actually I'm pretty excited about it. I think that this method, at least conceptually, mathematically, it does extend naturally to the multimodal case. Again, computationally, there may be some challenges to address. But conceptually, let's say you had 2 images as an input, just for an example, right? Then when you write down the input-dependent Fisher information matrix, it'll have a block diagonal structure. Right? So I believe if you push this over to the multimodal case, you'll be able to actually analyze not only the sensitivity within a given input channel, but also the cross sensitivity, which is something, again, I don't think that a lot of the existing methods naturally extend to.
For example, kind of like before I'm building the machine language model, there also have this kind of a cross-modal attention. They call it attention map, right? But I think this is also something trying to get like the cross correlation between the different modalities.
Yeah, that's right. Yeah, no, I think it's interesting. I think what will happen is in this, let's say the 2 input modality case, when you can still decompose your input into a sensitive and an insensitive component, but then if you look at the sensitive component itself, it also will decompose into 2 pieces, where one piece represents a sensitivity from its channel, and the second piece represents sensitivity that arises because of the presence of the other channel. So I think again, I don't want to get ahead of myself, but I think I'm confident enough to say I think there's something there. But I don't want to get ahead of myself. Okay, great. So this is just a quick summary of the steps. And by the way, I should also point out sooner than later, this is a joint work with my student Surya Sengputta, and he helped put together slides and did all the numerics, and he was great. So we start off with an input image X. We assume that we have a trained classifier, and we classify that image. We have access to the predictive distribution. We form the input dependent Fisher information matrix. We somehow determine the dominant eigenvectors or singular vectors of that matrix and the associated eigenvalues. If we want, we can threshold to determine the dimension of that task-sensitive space or use the rank of F. And then we can form the projection operators onto the sensitive subspace, the insensitive subspace, and then do our decomposition and then display the sensitive part as our visualization of our interpretability or the end result of our interpretability procedure. Okay, so let me show some numerical studies here. Again, these are just preliminary proof of principle, so please don't beat me up so much. There's a lot of work to do, and happy to collaborate with folks. So we considered a couple of cases. One where we used some open source medical images with the task of detecting cardiomegaly versus normal chest radiographs, and then in the second study it was more stylized, where we used brain MRI images as our background, and we created a signal detection task where we randomly inserted signals into the white matter. And then we basically it was basically a signal known statistically, background known statistically detection task. Okay.
What's the number of classes?
In this, I think in what I'm showing today is just two. These are just binary detection problems.
Like the rank, I guess, where the dimensionality is at most two,
Yes,
then it's like, I must be rank one then.
correct. Yeah, that's right. Yeah. So yeah, so but I think from a computational procedure, that's attractive for a binary problem that, the dimension of the task-informed subspace is low. So you just need to estimate the top singular vector of that matrix, right? You don't need to estimate the whole spectrum or a lot of them.
Why vector singular? Why did you say one and not two?
I'm just using the way it's two is limited.
Well, of the little bit of the grand matrix, but of the Fisher matrix, it's big.
Null space, side of the null space. The two by two. Both of
Well, I guess you'll let us know what your R is.
Yeah, I'm not sure. I will. It was either one or two. And I'll have to go back and check. Oh, I think it was one, but you go back and check that. Yeah. Okay. Oh yeah, another question. Yeah.
So it's stopping when
No.
I was gonna ask, how do you guys handle class imbalance, or you didn't have class imbalance? Because I mean, there was very few lesions.
Yeah.
And compared to the public, or that's not. The case.
Yeah. So in the MRI stylized case, we created a balanced data set. For the cardiomegaly, I forget what the imbalance ratio of there was, but yeah, that doesn't impact the procedure that we're following. Okay, so this is just a slide just summarizing the performance of the different classifiers that we trained. And we trained a couple of classifiers, or Surya trained a couple of classifiers. One was just a shallow CNN, the other was a VGG 16, and the other last one was a ResNet 18. So it's just showing, give you a sense for what the overall performance, the task difficulty was here. Just for context, so let me show you some results corresponding to the stylized MRI case first. And again, this is a simple case, but I think it's a really interesting case. So on the left column, these are examples of the true object, right? Corresponding to the signal present condition. So in the top and bottom row, these are two different examples, both corresponding to a signal present. And you can see the signal is enclosed by that red bounding box. Okay, and so basically in this case, using a shallow CNN, we computed the task-specific maps, which are shown in the middle column, and then the task-insensitive maps in the right columns. And what's neat is in the task-sensitive maps, you can actually see it picked up the signals, and it didn't pick up much of the background here, where the task-insensitive maps basically captured most of the background, but not the signal. So again, this is a very simple example, but it's an example that shows that this decomposition, in this case, it did a good job of separating kind of the informative signal from the background, right? So
I don't understand what the color is.
Okay, so the color is just for visualization. The color is just for visualization.
But I don't know the color map, so I don't know how to see what.
Yeah, right, yeah. I mean, do I, on the next slide, do I have it? On the next slide, I think I have a color bar, but,
Okay, is it jet or what is, what's?
yeah, so it was just color encoded, just for the sake of visualization. So probably we shouldn't have done that. But the thing to take home is, again, this is a decomposition. So if you look at the top row, if you literally add this image to this image, you get the original image, right? If you add this image and this image, you get the original image. So just, sorry for the misleading, display.
Just want to make sure.
Yeah, yeah. But it is myself and, okay, great. Okay. So here's another example. And basically this example is showing the impact of the choice of the classifier, right? So by construction, the task sensitive map depends on the classifier that was used, right? So that's not a bug, that's a feature. It has to be that way, right? So here's an example where I'm showing again those MRI examples, but now for two more expressive classifiers, the VGC 16 on the left and the ResNet 18 on the right. All right, so in this case, you can see the informative map. It still lights up near the signal location, but it's not just a clean little blob. It looks like the classifier was extracting information around the neighborhood of that signal blob as well. But for the VGG16, most of the energy in the task-sensitive map is still localized around the signal. But if we go to the ResNet 18, which is a deeper network, you can see there's still a lot of action around the signal, but then I'm not sure if you can see, but there is a lot of action elsewhere. There's still isolated network is looking at other places here where with a shallower network, the network is looking mainly at the signal location. So again, I think this sort of behavior is kind of well known, and deep networks behave strangely. They do weird things. But again, this is just a reminder that yeah, I mean, the sensitivity maps, they depend on the classifier as they should. Here are some examples using the chest X-ray example. Again, we have the true image on the left, which is an example of cardiomegaly. The task-sensitive map is the second one. The task-insensitive map is the third one. And then the last three are results from traditional post-hoc interpretability methods. So you can see the GradCam and the EigenCam, they're looking kind of at weird places where the task-insensitive map, the task-sensitive map has a lot of energy where the actual heart is enlarged there. So I'm not sure what else to say about that. But again, there's definitely disagreement between the traditional methods. But at least with the task-sensitive map, we know how to interpret it. We defined what it is, right? So we know how we can interpret it. And that's all I can say about that. And here are some more examples, again, corresponding to two different classifiers, the VGG16 and the ResNet 18. And the story here is similar to what I already showed you with that simple MRI case, is that when we have the deeper classifier, it tends to kind of look at many more places, where with the shallower classifier, the VGG16, a lot of the sensitivity identified was kind of near where the pathology is located. So again, this is kind of expected that you would have this sort of behavior. But anyway, at least our visualization, our decomposition method is kind of reflecting these differences, which we would somehow expect. Okay, so that's it for part one. So I want to get moving so I can use this new perspective for some other purpose. Maybe this is a good visualization or a good analysis method just by itself, but I want to use it for other things since I'm a reconstruction person. But just so a summary of this talk, we demonstrated a new theoretically grounded interpretability approach that was based on this input-dependent Fisher information matrix. We demonstrated it via some preliminary case studies. In essence, it's fundamentally different than traditional post-hoc interpretability methods, mainly because it decomposes the image itself. It doesn't just create a blobby heat map. It's literally an image decomposition based on kind of the local predictive sensitivity of the model. And there's things you can do with this. For example, the task-sensitive components can be evaluated through perturbation and reclassification experiments. So there's things you can do. If you're able to decompose your input, there's just things you can do that you couldn't do before. And again, that's beyond what I'm presenting today, but I just wanted to mention that. And we think that this sort of framework may be also valuable for auditing whether a model is responding to true disease structure or doing some sort of shortcut learning. But again, this is to be explored. Okay. So I'm about halfway done with my time, maybe a little bit more than halfway done with my time. So let me switch gears and we're going to talk about hallucinations and image reconstruction. So I know we have experts in the room, so I'm going to go very quickly on the background, but I have a few perfunctory slides just defining the problem that I'll show you. We'll go through them extremely quickly. I'll define what I mean by an image hallucination in this talk, and then we'll use that machinery I just talked about for analyzing null space hallucinations. And upfront, I should mention this is a joint work done with another one of my students, Muzaffar Osby, and this work was recently presented at the SPI medical imaging meeting, and we're moving forward to write a journal paper on it. Okay, so I'm going to assume in this talk that we have a linear model that describes our imaging system. So we have a linear forward model, G equals HF plus N. G is our measurement data. F is the object property we want to estimate. H is our forward operator. Okay. And we all know that in the problems that we care about, we can't just directly invert H. The problems we care about are ill-posed. We need a way to circumvent that. And the natural way is to learn some a priori information or to constrain the problem some way to mitigate its ill-posed nature. Okay, so let's talk about hallucinations in tomographic imaging. And before I go on, I should mention I have a citation on the bottom. I guess boy, time goes by quick. It's already 2021. But so about 5 years ago, we published a paper where we proposed just some definitions and how should you define a hallucination within the context of tomographic image reconstruction. And that's relevant to what I'm talking about here. So in high level terms, hallucinations correspond to reconstructed image components or image features that cannot be stably recovered from the measurement data. That's the definition I'm going to be using in this talk, although this is a little bit of a relaxed definition from the one I proposed in that paper. And I'll explain a little bit more about this as we go, right? So you can view this a hallucination as a type of reconstruction error, but it's a specific type of reconstruction error. There's many different types of reconstruction error. This is a specific one. I'll talk about that more in a minute. But this is very relevant to when we have incomplete data and we're trying to recover an object, right? There's a null space. We don't have unique identifiability and all of these things, okay? So what are the contributions to reconstruction error, right? So we have our measurements, data. If we don't enforce data inconsistency, that can result in errors in our reconstructed image. If there's modeling errors, that can result in errors in the reconstructed image. If it's a statistically grounded method and we assume something wrong about the statistics, that can result in errors in the reconstruction method. Or again, if we have an explicit prior and we rely on that prior too much, that can result in image reconstruction errors. And that red box, that's what I'm referring to as a hallucination in this talk, when we basically rely on the prior too much and the prior doesn't give us the correct guess for the null component of the object. Okay. So let me just make sure everyone's on the same page in terms of terminology and null spaces of forward operators. So again, let's just consider we have a simple forward operator. I'll neglect noise here. G equals HF. And let's assume we have incomplete measurement data. So we have a null space. It means only part of the object is effectively visible to the imaging system, right? And so the null space of H is a subset of the domain of H that corresponds to all of the objects F that map to the zero measurement vector under action of the forward operator, right? So the null space characterizes all of the stuff that the imaging system can't see, right? So that's concerning to us, right? As at least in medical imaging, it means somehow we need a way to estimate that. And just from basic linear operator theory, we know that we can decompose any object in the domain of H into two pieces. We have an orthogonal decomposition. We can decompose an object into a measurable component, and that's the component that the imaging system can see, right? That maps to some non-zero data vector. And then we have the second term, which is the null component. And that's the component of the input object that's invisible to the imaging system. Okay? And that's what we have here, right? So when we try to get a good estimate, or when we try to recover our original object, this invisible component, this null component, it's informed by the assumed prior, right? There's no information in the measurement data by definition regarding the null component, right? So this is a thing that I've been talking to several people today and kind of getting on my high horse, especially with the students, right? So just for the students, I want to make sure everybody understands. When you're using a learned reconstruction method and trying to recover an object from highly incomplete data, you are basically trying to guess at this. Literally, that's all you're doing. You are guessing at this. Don't tell me you're doing anything else. Right. So we need to be careful about, yes, okay.
Already, no, you don't have information of the null cause space.
Yeah.
That's what output you want to get. You know you are just to make a guess. Then what information you want as an output?
Well, I'm not sure. I mean, so what I say, so your guess is conditioned on the measurable component, right? It's not a random guess that the algorithm is making. It's conditioned on the measurable component if you're doing something sensible, right? But my point only is that, just because of the way the world works, there's no information in the measurements about this part of your object, right? And this is the whole motivation for using a prior. We want to somehow recover that in a way that's consistent with our statistical assumptions about the distributions of objects that we're imaging.
Those have the other information from the observation that you can also have some information from the of the space to make the
Yeah, right. You can, yeah, exactly. Well, you could, in a loose sense, you could call that a prior. I mean, if you're a reconstruction scientist, and if we're being a little bit imprecise about language, a prior. It could be any constraint. It could be a constraint. Any information you're using to inform your reconstruction. Although in a strict Bayesian sense, the prior means something specific. Yeah. Okay, so anyway, that's life though, and that's what we're doing. I mean, I'm not saying we shouldn't try to guess that, but when we do try to guess the null component, we just need to be a little bit careful because something could go wrong. We probably should be safe to assume something will go wrong, right? So we need tools, we need ways of analyzing the performance of reconstruction methods so that we can refine them in ways that we have some sense they may be ultimately trustworthy for certain applications. Okay. Okay, so now that we're on the same page in terms of that notation, so let's assume we reconstruct an image, whatever reconstruction method you want. I don't care. It could even be a traditional method. We reconstruct an image. I'm going to call the reconstructed image F hat, but that's what comes out of our reconstruction network or our reconstruction method. So we know we can always decompose F hat into, again, two pieces, one piece that's projected onto the measurable subspace, one piece that's projected onto the null space of the forward operator. Right, so we have this orthogonal decomposition. And in principle, we can compute or we can form that projection operator P null, although for high dimensional problems, again, it can be challenging. Okay, so in this talk, again, just to follow up on my previous comment, I'm going to refer to any component of the reconstructed image that lives in the null space. I'm going to refer to that as a hallucinated component in this talk. Okay. That could potentially be relaxed, but just for terminology. And if you push me on that, why did you do that? You know, I did that because I think with high probability, stuff will go wrong in the null component. High probability. I mean, there are regimes where there are guarantees of exact recovery, like compressive sensing. We were talking about there are under certain conditions, there are regimes where, yes, I know I can do that, but those are special cases.
Why don't you just project that as the component? I don't know much in image.
Why didn't I what?
Why not just compute F naught and subtract it from F hat to show?
I'll show the measurable component.
Yeah.
That's an entirely reasonable question. That's right. So that's what the pseudo inverse would effectively give you. Like if you have a linear forward operator and you compute a pseudo inverse or some regularized version of a pseudo inverse operator, that's what it would give you. And so that's the honest way to do it. Right, that's the honest way to do it. So then basically you would have an image that doesn't look good. Right? So visually it's going to be blobby, it may look like a mess, but you can trust the hell out of it because you know that that image came directly from the data. Right. So, but we like to do a little bit better, right? If we have information about the class of objects we're imaging, we'd like to use that information to do a little bit better. But the question is, if we get too greedy and we try to do too much, then bad things can happen. So we need ways of analyzing this process.
Measurement system like H kind of almost something like that.
Yeah, for example, here we're considering ill-posed problems. So your forward operator, let's just for sake of argument, let's assume H is undersampling your data. Yep. Yep. Okay. So how do we analyze these hallucinated null space components in a task-specific way? So let's consider that our reconstructed image is going to be used in a downstream inference task. Let's say it's going to be used to classify a signal. Again, for simplicity in this work, I'll just assume that there's a downstream binary classification task. So our pipeline is reconstruct an image from undersampled data, maybe use a prior, get some beautiful looking image, then plug it into a classifier and see how useful it is. Okay, that's the pipeline. And then in the clinic, these are a type of pipelines that people consider. So the key question now is, we know that the hallucinated component, it may be diagnostically useful. I mean, if things go well, maybe parts of the image that were recovered in null space, maybe it will help the downstream classifier, but some may not help, right? So in general, hallucinations can be either helpful or harmful. You can't really make a strong claim that's universally good or bad. It really depends on what the downstream task is. Okay? But up until now, there's been no way to analyze. There's been no way to address this question, right? So this is what we seek to do. We want to kind of isolate and then analyze the hallucinations that are produced to see what the impact is. So again, like I mentioned, let's assume our downstream classification task is just a simple binary classifier. All right. And so our strategy now, we're going to combine the null space structure with that task sensitive subspace we introduced in the first part of the talk, right? So we already know that, at least in this talk, we're going to consider the null space components to be hallucinated, even though, yes, I'll give you, there's a non-zero probability some of those components might be right, but let's assume that they're hallucinated. So we have our null space, and then we're going to define this new task subspace, which again, we already know how it's going to be defined because I told you in the first part of the talk. And then we're going to project the reconstructed image onto the intersection of these two subspaces. Right. So essentially, let's consider here just a simple schematic Venn chart. So we have our domain. This is the input space of our forward operator, the domain. And then we have a subspace of the domain, which is our null space, right? The parts of the object or the objects that are invisible to the imaging system. And then we're going to have our task sensitive subspace. And then we're going to compute the intersection of those two subspaces. And we're going to project our reconstructed image onto the intersection of those two subspaces. And when we do that, it's going to tell us which parts of the reconstructed image were simultaneously not supported by the measurements, yet still important to the downstream classifier. That,
Stage, the part one T would function a network, not of the images.
yeah, that's true, actually. I mean, you're right. Probably that notation is not good. Probably that's a typo. That you're right. You're right, Jeff. Yeah. I think you're exactly right. I mean, in a sense, it's indirectly a function of H, right? Because a reconstructed image, but your point's taken. Okay, so then I can go quickly through this because we already talked about this in part one. So how are we going to do it? We're basically going to repeat what we did in part one, but now the input to our classifier is not going to be X, it's going to be our reconstructed image estimate F hat. So we'll compute the input dependent Fisher information matrix with respect to the input F hat. And we'll do all of the machinery that we talked about in part one, right? We'll identify the dominant eigenvectors, we'll define the subspace, that defines the sensitive directions, and then we'll have our subspace. So again, we already know all of this. So again, we can take our reconstructed image F hat and we can decompose it into two pieces. One piece that's projected onto the sensitive subspace and the other piece is projected onto the insensitive subspace, right? And again, I think we talked about some of these issues in the first part. So again, finally, like I said, these task-sensitive hallucinations reside in the intersection of the null space and the task-sensitive subspace. And again, yeah, these are kind of hallucinations that were informed by the prior, not supported by the data, but the classifier still leveraged them, right? These are components that were sensitive with respect to the classifier. Right. And again, to compute the projection onto this intersection, we can just do an iterative orthogonal projection procedure, which I believe converges because both of those subspaces are finite dimensional. So let me just show some very preliminary numerical studies of this. I think I'm almost out of time, right? So again, we utilize this a virtualized kind of a stylized or imaging procedure using MRI backgrounds with samples embedded. For the forward operator, I consider just a undersampled MRI or a stylized MRI where basically the forward operator was a Fourier transform that was undersampled. So I'm not claiming that I'm modeling the MR physics here at all. And we trained learned reconstruction methods to get our estimates F hat. Okay. These are just some examples of our objects that were imaged. Again, the top row here shows examples of signal present images where we randomly inserted signals into white matter. The bottom row just shows examples of the signal absent images, right? Again, our downstream classifier is trying to distinguish the signal absent from signal present images after we reconstruct them. Okay, so here are some examples. So let's look here. The reference image is in the top left, and then each of the three columns next to it correspond to images reconstructed using a different learned reconstruction method. And I won't go into details there, but each of these three columns correspond to two different learned reconstruction methods. In the red bounding box, this is showing zoomed in regions where a true signal was present, right? These are signal present. These are true positive examples I'm showing you. And then the blue bounding boxes shows examples where there was some false signal inserted by the reconstruction method. So you can think of that as a hallucinated signal, right? So our reconstruction methods kind of accentuated the true signals, but in some cases it inserted false signals that shouldn't be there. And that's what I'm showing there. In the next row, these are the null space hallucination maps. So in other words, these are the null space components. If you project your reconstructed image onto the null space, you get this. So you can see there's a lot of structure there, kind of hard to interpret. But then if we compute the task relevant null space hallucination map, we get something that's much more interpretable. So in all of the task relevant NSH maps, we see the true signal lights up. But in reconstruction method 2 and reconstruction method 3, there are also some false positives that also were showing up in there too. And on the bottom, it just shows an overlay of the detected signals with the true object.
Why is it a good thing to show up in the hallucination map?
Why is it a good thing? Or
Recon, just by the name of that it's a hallucination?
well, in this case, so if you look at reconstruction method 1 and you look at basically here, right? Oh, I just happened to be pointing to it. Right. So if you look at it, this block here actually corresponds to the location of the true signal, right? So this is basically showing up as a hallucination because the reconstruction network artificially enhanced that signal.
Then that's a false.
But these were true positive. These were true positive detections.
Then
So
it shouldn't show up, right?
What's that?
And you'd like it to be the opposite. Good example for the true one to not show up in the hallucination map.
Well, no, so here it depends how you define good. Here, if you define good as the classifier made the right decision. And what this is showing, it's showing, okay, our reconstruction method, it enhanced the signal, resulting in a hallucination, but that was a useful hallucination. It made the signal easily detectable by the downstream classifier. Right. Where here, this is interesting. So these are all true positive decisions, but it turns out that in these other cases, there were like multiple signal-like hallucinations that were produced, but the classifier still ended up making a true positive decision.
How would a clinician, they looked at the NSH map?
Well, I'm not suggesting at all you show this to a clinician. So this is basically an analysis tool for an algorithm developer to get some insights into, are hallucinations being produced, which ones are useful, which ones are not. So this is an early stage technology development type of analysis. I'm definitely not proposing to show this to anybody wearing a white coat. Not yet anyway. Here's examples of false positives, where the actual object was signal absent, but the downstream classifier said, oh, there's a signal in there.
Same construction methods?
These are the same 3 reconstruction methods. Yeah. No, none. Sure. Send me that. I'm happy to test yours. Happy to test yours. Yeah, these are 3 different reconstructions. Basically, they're all kind of just some simple end-to-end unit method, but the loss functions are different. Where there's like a task enhancing component to the loss function. I don't want to think to it. Yeah. But here, if you look at the task relevant null space hallucination map, boy, it's chock full of stuff. It's chock full of stuff here too, right? So there are a lot of small blobs that look like signals showing up here. And this resulted in tricking the classifier. That's why the classifier ended up making a positive decision, even though it was a signal absent case, because a lot of the hallucinations looked like blobs. Our signals were blobs, and there was just a bunch of them that were produced in this particular case.
Bright red here means the same thing as bright red. I mean, were they all sort of shown on their own, 0 to 1 in the red channel scale, actually. Should I confirm brightness of the red here?
Yeah, that's a good, I think you can, but I need to verify that. Yeah. Okay. So then, yeah, just to wrap things up here. So just one other result. So we know, just like in the first part of the talk, we would expect the task-specific null space hallucination maps to vary with the classifier and the task involved. Again, it has to be the way. It's not a bug. It has to be that way, or none of it makes sense. So just to show an example, again, I'll just use a shallow CNN as the downstream inference model, and then I'll use an adversarially robust, fine-tuned using projected gradient descent model, right? So basically 2 CNNs, but trained differently, right? And the reason we use the adversarial robust one, I don't know why we use it because when you do adversarial robust training, typically the features that the classifier learns are more aligned with human interpretation. These are less brittle classifiers. They learn features that somehow seem more interpretable, where just a traditional CNN trained with a traditional loss, I mean, they're dirty fighters. They'll use whatever weird features they need to do it. So we just did it to see what would happen, right? And here's an example. This is, again, a true positive case. So there was a signal present, and we have a reference image here, and then we have the example of the reconstruction here, right? And again, we have the informative, sorry for the typo. We have it, this is a sensitive null space map and then the insensitive one. And this is corresponding to the standard classifier. On the right is the robust classifier. So you can see for the robustly trained classifier, you see a hotspot in the middle of the red box where the true signal is. And there's some other stuff in the background, but not that much. But with the standard trained classifier, you also see a hotspot where the true signal is, but then you see these hallucinated blobs here. So it turns out in this case, the standard classifier made a wrong decision. It was tricked by these other hallucinations where the robustly trained classifier was not. Right, just as an example. So let me summarize this part of the talk. So we just kind of reviewed that hallucinations can occur when attempting to address ill-posed inverse problems in imaging. Null space hallucinations are unsupported by the data, and by definition, they reside in the null space of the forward operator. Not all hallucinations are going to impact the performance of a downstream task. Some will, some won't. So what we've done here is developed a method to identify the subset of hallucinations that impact downstream task performance that you could subsequently analyze, and this might form the basis for other types of quantitative analyses. And we did this by using the interpretability method I showed in the first part of the talk, where we introduced the input-dependent Fisher information matrix and defined an explicit sensitivity subspace. And so that was kind of the enabling technology here. We just combined that with the fact that, hey, we know what a null space is, and this was like a gift for free. So again, this is preliminary, but we do think that at least these sort of perspectives are new, and they may enable new assessments and refinements of learned reconstruction methods. And I think there is a need to think carefully in how we analyze these type of methods. So yeah, I'd just like to thank Soria and Muzaffar, who really did a great job pushing these forward. And thank you again for the invitation. Happy to take any remaining questions if there are any. Thanks.
Give a scale of the hallucinate space being no intersection as subspace.
So that's a great question. So that's an interesting question. I mean, I don't know. I mean, it depends what your goal is. I mean, if the hallucination is beneficial to the downstream task, then you'd want that to overlap. So again, we considered, a special reconstruction method here where we wanted to promote. If there's a true signal present, we wanted to promote it so it's easier to detect. So if you have a reconstruction method that artificially enhances true signals, resulting in some energy in the hallucination map, that might be useful. So I mean, it's just interesting, and it really depends on what you want to use the images for. Right. I mean, ideally, in the ideal world, you might argue, well, we don't want any hallucinations, right? But I'm not sure that's a realistic expectation if you're really solving an inverse problem with the prior.
So if that basic measure possible that can be used to update your system or update your classifier.
What you're asking if you can kind of refine the classifier?
Yeah. Maybe the system.
The system, which of the imaging system, or which part? Are you talking about part one of the talk or part two of the talk?
Like the imaging system and
Yeah.
classifier.
Oh, yeah, sure. So absolutely. I mean, that's part of the potential value of this analysis, right? If you're able to identify and determine the impact of hallucinations, then you can change things. If things aren't going your way, then what you said is exactly one of the potential uses of this, right? If your hallucinations turn out to be harmful for your downstream task, then you can either acquire more data so you don't rely on your prior so much, or maybe constrain your inverse problem better, or revisit your design. Yeah, I agree. That's a great point.
I was gonna ask, how big is the classification network in quantum? And it's a binary classifier, right?
Yeah.
And when you say adversarial robust, was adversarial training used?
Yeah.
Okay.
Yeah, and these were relatively shallow CNN type classifiers in part two.
Yeah, I'm curious, could you or have you explored using this method to make classifiers that are robust to different reconstruction potential hallucinations, or like potentially train pairs of classifiers with particular reconstruction methods to kind of focus on this true signal that I'm listening to?
I absolutely have not, but that sounds interesting. Yeah, so that sounds like that might be fun to think about.
So the single coil MRI is the kind of perfect first case for this, because if you use unitary DMT, the singular values are all one
Right, yeah.
or zero. So you can clearly define null space. But I know that you and I work on problems where
Yeah.
the spectrum is like 1 over
Yeah,
you
yeah.
know, frequency. So
Yeah.
what are your thoughts about how to apply this when you kind of don't have a clear cutoff of where it becomes the small space is very, very reduced instead, right? Or whatever.
Yeah. And that's an important problem. So I think your MRI, as you mentioned, that I think could be within the reach of this. And even if it's not single coil, I think, estimating the null space of modern MRI systems, I think that's not unreasonable, right? So MRI could be applied there. But if you want to apply it to like a 3D CT system or something like that, now that's a challenge, how to compute a null space projector. Right. And we in my lab, we've thought about these problems and we have some approaches, but I don't, as far as I know, there's not a great solution to this.
I don't even mean the computational problem. I just mean even the definition given.
Sure.
It's kind of declared slowly.
Yeah. Right. Yeah. I mean, I think that's something to be explored, right? I mean, you could determine a threshold just like when you regularize an SVD, but that's something to be explored, though. Yeah.
And then one other question about the multimodality. Let's take the maybe simplest version of that, which is color images, some color imaging system. So you've got RGB channels. I may have misunderstood you, but I thought you said that the FIM would be block diagonal, certainly a block structure, but I don't get the diagonal.
Oh, yeah, maybe, sorry, I misspoke. It's block structure, not,
Block
yeah,
structure.
yeah, sorry.
Okay.
Yes, correct. Yeah,
I wanna make
thank
sure
you.
it
Yeah.
wasn't something independent.
No. Yeah. Yeah.
And one last question
Yeah.
from me. So this, the linear decomposition here, what about if you have, like we have in CT, a non-negativity string? So your thoughts about how you might read that into this?
Yeah.
You get information that's not as nicely represented in your algebra view, right?
Yeah, no, that's also a great question. Yeah, I've thought about that in the past. I mean, I'm not sure at the moment I have a good solution for how to incorporate that. But yeah, I mean, I've thought about that, how to, in one sense, you could also ask, how can you, how can you perform an SVD of a system if you know you're going to be incorporating some constraints? So yeah, I think that's open work.
Any other one? No, let's thank Mark one more time.
That's
Actually,